Good day, ladies and gentlemen, and welcome to the CUAHSI Cyberseminar conference call. My name is Erica, and I will be your coordinator for today. At this time, all participants are in a listen-only mode. We will be facilitating a question-and-answer session towards the end of the conference. If at any time during the call you require assistance, please press star followed by 0, and a coordinator will be happy to assist you. I will now like to turn the presentation over to your host for today's call, Mr. David Kerstel. Please proceed.
Thank you. Folks, welcome to the second cyber seminar of the fall of 2008. Today's presentation is by Cecelia DeLuca from National Center for Atmospheric Research. Before we get going, just a few quick announcements. My name is David Kerstel. I'm the program manager here at CUAHSI. And if you have any questions, as you heard earlier, you can contact the operator, or you can send a chat message to host over on using the chat windows over on the right side. And we'd certainly appreciate any comments, criticism, feedback, etc. about the seminars. You can send that to commanager@cuahsi.org. About the middle of the next week, if you want to spread the word on this, the seminar is being recorded. And it will be available over the web probably around the middle of next week, and that's at cuahsi.org/semcurrent.html. Upcoming cyber CUAHSI activities, we have 2 more cyber seminars scheduled for the fall. On November 7th, we have Edward Rutherford from the University of Michigan, and then on 14 November, we have Aris Georgakakos from Georgia Tech. Also, I'd like to remind folks that there will be a CUAHSI member get-together and reception at the fall AGU. I don't have the time and date yet, but we will certainly make that information available to you. And I'd like to introduce today's speaker. It's Cecelia DeLuca. She is head of the Earth Systems Modeling section at National Center for Atmospheric Research, and she'll be talking about ESMF, Earth Systems Modeling Framework, and Earth Systems Curator, an integrated modeling infrastructure for virtual communities. And I will now turn the presentation over to Cecelia.
Okay. I'm waiting for the ball to drop.
Yep,
okay, there it
yours.
is. Wonderful. So thank you. Thanks for the introduction, and thanks very much for the opportunity to talk to you folks today. The Earth System Modeling Framework and Earth System Curator are projects that have been around for a while. ESMF's been around for about 6 years now, and Earth System Curator for about 3. So I'm going to be doing a sort of general overview of both of the projects and where they are right now. We move to the next slide. What we've got to offer, what we have going on, and what our priorities are, or what some of our collaborations are, what our the project status and funding status looks like, and what we're planning for the future. Okay, let me use the arrows instead. Everyone can see this. Everyone can see the slides, okay, right? So what ESMF offers is really the main thing is model coupling, and that's either through user-supplied interpolation weights through a package like a script from Los Alamos, or through framework-generated interpolation weights, which were out in our last release. We have efficient data transfers on parallel computers in order to do the sparse matrix multiply that's behind that kind of grid transformation. We also offer a model architecture. So with ESMF, it's a component-based architecture. There are wrappers for components that some people have chosen to implement down to the parameter level and or to the parameterization level, and others used mainly for large-scale components like atmospheres and oceans. It is a hierarchical structure within the architecture so that components can be nested within other components. And we don't have one big coupler in the middle. Usually folks create a bunch of couplers at the different levels. We offer a bunch of model utilities. There's a very extensive calendar management package with all kinds of calendars in it and time functions logging and communication libraries. We also offer, which is new, the ability to write out descriptions of particular of components or fields or bundles of fields in XML or in plain text, and to ingest those descriptions into a portal and have them display so that you get either a documented model distribution or a documented simulation. So the way ESMF works is really pretty simple. There are only 3 ESMF component methods. There's an initialize, a run, and a finalize. And users split their code into these 3 pieces, and you can have different phases. You can have multiple initialize phases and multiple run phases. But basically, there's got to be an initialize, run, and finalize that are discrete. And you sign these up to be methods of an ESMF component type through a registration process. But then we've got the methods, your custom methods within a generic framework, and we can run them within a generic driver. So the ESMF components that you've set up call back into your user-specified methods once that driver is activated. And the initialize, run, and finalize methods cascade down the tree of components. So what you see over on the right is an application that's a hurricane model where you've got an atmosphere and an ocean coupled together with an atmosphere-ocean coupler. If you call initialize from the driver, it propagates down the tree. So it'll initialize the parent, and then the parent will go ahead and initialize its 3 children, the atmosphere, the ocean, and the coupler. And likewise with the run, when you call a run from the top level component, it goes down and sequences and drives the 3 components, the 3 children components that are beneath it. And some groups have set up very extensive trees like this that have 7 or 8 levels of components going down to very small, again, to pretty small parameterization. There's that call ESMF comp run there is what the standard interface looks like. The run is the same, that the initialize, run, and finalize all have the same arguments. It's your component, pointed to your component first, an import state, which is all the fields that are coming in, an export state, which is all of the fields that are available after the component has run. There's a clock. There's that does the sort of start time, stop time, time step, any other controls that have to do with timer in there. There's a phase, and that's if you want to have multiple initialize methods or multiple run methods or so on. And there's a blocking flag that describes the way that the components are sequenced. Okay. So in order to set up your data in ESMF and register your components, you need to be able to describe the data that you have within ESMF data structures. And we have 2 options for doing that. The first is a very general, very general option that's just an index-based array. And you can use this for everything from unstructured grids. Some of the hydrology folks in the Army that we've worked with have done that, to multi-patch logically rectangular grids. So the basic data structure is 1 or more logically rectangular tiles that store indices in a topology. The operation that you can perform on this data structure, or the main one, is the sparse matrix multiply for regridding. And the user needs to supply their own interpolation weights there. And the operation that we have implemented with this data structure are highly scalable. So there's no global information held locally, and it uses a distributed directory approach that comes out of Sandia that is very efficient for very, very large processor counts. We have folks that want to run out to tens and hundreds of thousands of processors and want to make sure that they can do it with the software. So the second kind of representation that we have is in physical space, not in index space. and this is built on the underlying index-based layer. But it also includes either logically rectangular or mesh, unstructured mesh information. And with this approach, you can generate the interpolation weights from within the framework. You don't have to go off somewhere and try to generate your own and attach them to the sparse matrix multiply. So this is a capability that's come relatively recently online for us. The ability to represent meshes has come online relatively recently for us. And we're just starting to have users begin to explore this capability. Okay. So this slide outlines some of the coupling options that are available through ESMF. You can do a single executable, and that's sort of our default configuration where everything's compiled. All the components that you have are compiled into the same executable. You can also set up multiple executable configurations in ESMF, and there are a couple of different ways to do that. Coupling communications can be set up and called from within a coupler, which is the way that the climate community would typically do this. Or the coupling communications can be set up in a coupler but called directly from within components. And that's useful when the data transfers are sort of deeply embedded in the component. And this is appealing for one scenario where people have found this appealing is when they're doing I/O. So you can set up where you want your I/O to go at the higher level of the coupler, and then just send it off from deep within the component. We support recursive components for nesting higher resolution regions. So that's something that the National Weather Service has been playing with and is interested in. If you wanted to refine the grid, for example, of a component, but consider it the same component and consider it a nested subregion within the parent, you could do that. And we also support ensemble management, including sequential execution for ensemble members, which is kind of hard if you're in the same address space and you want to run multiple components within the same address space sequentially. You need some way of setting up your component and being able to distinguish different internal states for different instantiations of the same object. I hope that makes sense. Ask me later if it didn't. So our port and test status is that we've got about 30 different compiler and platform combinations that we're regression testing with nightly. New ports include G-Fortran and Solaris, and we're currently working on a Windows port, actually, with the new Cray Windows platform that's come out. This link takes you to a very extensive platform list. On our website, if you go to this link, you'll see exactly what environment variables you need to set to run on that platform. And we also have the output from our suite of regression tests. We run a couple thousand regression tests every night on these platforms, and when we do a release, those are also out on this web page. So you can check what you get together to make sure that you're running successfully. We have also started running on a TerraGrid. We got an award to use the TerraGrid build and test service to access additional platforms for testing. So that just started in August, but we started doing that. And we also have a new test harness with the meshes that we have. We have also an observational data stream class, and we have our logically rectangular grid class. We have a really enormous parameter space to test. And so we implemented this test harness that takes an abbreviated, a string that has an abbreviated syntax so that we can compactly specify different grids and different distributions of those grids. And that helps us to automate the testing of that really enormous parameter space. Okay, so a couple of slides on performance. The first, the graph on the top is the sparse matrix multiply with ESMF compared to the MCT package, the model coupling toolkit. MCT really just works at the index-based layer, and like the index-based version of ESMF, you have to supply external interpolation weights. It's kind of hard to see that graph, but it's going out to 8,000 processors, and it shows that ESMF is basically tracking the MCT performance pretty closely. Since this graph was developed, both the ESMF and the performance, I think, of both the ESMF and MCT have improved. But if you wanted to get updated reports on performance, they're on the web, and that's the link. We have 7 or I think we have 6 or 7 up there. The slide on the bottom is memory on platforms like BlueJean. It's always a challenge to keep the memory down, and as you go out to very high processor counts. So this shows 4,000. More recently, we've been going out to 16,000 processors on those platforms, and we've been working on reducing our memory footprint. The yellow line was what we were at before some recent optimizations, and we've been shrinking that down to the lines below. Okay, so what we've got in progress, the parallel regridding, as I said, was new. This is based on an underlying, basically both our structured grids and our unstructured grids. Everything goes through the same parallel regridding engine, which is based on an unstructured mesh package, which is based on an unstructured mesh package from Sandia called Sierra. Excuse me. It's 3-dimensional, so we can do interpolations in up to 3 dimensions. We can only do bilinear and higher order methods through this approach. So we're looking at a different package for doing conservative regridding. But with this, we can do grid to mesh and mesh to mesh and grid to grid interpolation. And we also have some niceties implemented for dealing with pole issues for spherical grids. And of course, that's a common problem for our domain, at least for the global modelers. And if you want me to talk more about that later, I can. Okay. So the Earth System Curator is the sister project to ESMF. Curator is designed to link data sets with a detailed description of the model that ran to produce the data set. And some of the reasons that you might want to do this are to describe models, to document them, not only the top-level model, but also all the components in the model, to do archival and search for models and data sets. So in a portal environment, you might want to browse and look for a particular type of component that's out there. And finally, for model intercomparison. So one of the first deployments of the portal that we developed for Curator was for a workshop here at NCAR, a summer colloquium that compared 13 different atmospheric dynamical cores. And I can show you the prototype portal in a couple of slides. This project is in collaboration with the DOE Earth System Grid Project. That was the portal that served IPCC data, GFDL, Georgia Tech, the British Atmospheric Data Center, and some other French and some other European partners, Surfax and France. And the group, the Europeans have a big project going called Metaphor that's developing climate and other Earth system model metadata. So we've been collaborating closely with them to come up with schema that work for describing data and describing models. So long term, this kind of a portal is appealing for its ability to do compatibility checking before coupling components, for automatically generating coupler components where that's possible, and also for loosely coupling models using web services. So I don't have much of it in this slide because it just started, but one of the things that we've been doing recently is working on automatically generating web services, a web service interface from the standard ESMF interface, which I think is going to be really appealing for our users in the longer term because they'll be able to use the standard interfaces that they have either for tight coupling on the same high-performance computing platform or in a loose coupling scenario where they may be going across institutions and different computers. And also maybe introducing their modeling components into a heterogeneous environment where there are visualization services or steering services or whatever other services. Okay. All right. So one of the challenges in sort of building up a semantic portal for storing components and data sets and enabling people to use the information that's in there is actually, I mean, you guys probably all know this, collecting that metadata, that's really hard to do. People hate, having to sit down and write exhaustive text or XML files, and even a browser, even a form interface for that is pretty painful. So what we recognize in ESMF is that the framework itself, especially if you're working at the physical space layer, holds a lot of information, excuse me, about grids and fields. It holds information about how components are connected to other components. And the user doesn't have to write that themselves in order to describe the system. So what we built into ESMF were are standard attribute packages that hold some of this metadata, either from some of the pieces of the metadata are from the climate and forecast conventions. Other pieces are what we've been working jointly with the Europeans on. And that attribute package within ESMF can export metadata in an XML format. And it can be ingested into this version, a new version of the Earth System Grid, which then propagates it. And I think on the next slide, I don't know if I explain how. The diagram at the bottom shows how it gets ingested and transformed into a bunch of different layers of objects. It gets transformed into Java objects, which end up in a relational database, and then the relational database converts it to RDF. And if this is just gobbledygook, at least I'll get through it quickly. But the RDF enables some reasoning to be done. The RDF is a triplicate format where you've got the subject, basically a relationship, and an object, and it enables some reasoning to be able to be done with that information. So it gets represented in RDF as well, and then it gets propagated to the portal interface, where it can be browsed and searched. And we also implemented the ability to create a dynamic comparison table, which was useful for the DICOR workshop, the atmospheric DICOR workshop, because people could select what DICORs they wanted to look at and then select what specific properties they wanted to look at of those DICORs and dynamically create tables to do that. You probably all know what XML looks like, but that's basically what comes out of ESMF, a very abbreviated version of it. And here's a quick look at the portal. I think I'll have enough time to do this, so I'm going to try to switch over into sharing my desktop. A little disconcerting to do this without hearing anything from anybody, so hopefully this is successful and you're all able to see this. Yes?
Yes, this is David. Yep, it's up and running.
Okay, great. So this is the portal that we set up. I'll show you what the search looks like. So for example, this is mainly set up for the DICOR information that we collected. But if you wanted to look at model components and look, say, at the numerical method and look at the vertical coordinates, you can pick, let's say, let's look at finite volume, and let's look at height coordinate. And we'll submit that query, and that'll bring up just one of the models, one of the dynamical cores that was implemented. And here are the properties of that DICOR. So again, what we're aiming for with ESMF and Curator and the Earth System Grid Link together is the ability to, as much as possible, get this information out from the framework and have it automatically ingested into the portal, especially the grid information. And it's all displayed here. You can expand or contract these descriptions of the component. Those are the scientific properties. It's also connected to the outputs, so you can see what the component is producing. And the other properties are still pretty simple at this point. I'll show you one other thing. Oops. Going back to the search so the dynamical core components that we were working with were just a single component. But we have some models that are using ESMF that are deeply nested and contain many components at this point. So I'm just going to look at atmospheres and look at GS5. And here we're using this sort of standard hierarchical structure within ESMF to construct to reconstruct that structure within the portal. So you can see the top level GS5 atmosphere. You can see, if you shrink this down, that it's really just an ocean and an atmosphere component within it. And you can expand each of these to see that the ocean component, for example, can contain either MOM4 from GFDL or can contain a GS5 ocean component. If I click on that, it would take us over to the MOM4 pages. And if you expand the atmosphere, you can see the many components, ESMF components that are set up within the atmosphere. So each of these links, the GEOS anyway, is a separate ESMF component. Okay. I think I'll go over to, this is the general page for this symposium. This, for example, is the comparison tool, which was set up specifically for in this case, for the dynamical cores that were there. You can see them over on the left. If we pick out, say, 4 of them and take a look at some of the properties of those components, we can set up the table and compare them dynamically. And the eventual goal for this is that, as the database here gets built up, as more components are added, and as more experiments and symposia and comparison projects are added, that you can actually begin to look at components across not just the same project, but also across different sorts of projects. Okay. And you can do an export to Excel, which is kind of nice, because some people, I mean, for charts or whatever you want to do. Okay. There are some other nice things in there, like linking between the model description to the simulation and the data set, and looking at specific experiments. But I think I'm going to go back to sharing. Okay. All right, good. Well, that was successful. And so, moving along. Who's using this right now? So, this is really mainly ESMF. That portal that I just showed you is pretty new and was just used for the symposium this summer. But there's a group called the National Unified Operational Prediction Capability, which is basically all the U.S. Earth Science Operational Centers. It's the National Weather Service at NOAA. It's Navy, FENMOC, and CENMOC. It's the Air Force Weather Agency. And they have agreed initially to standardize on using ESMF as their sort of technical foundation at the level of high-level components, plus such as oceans and atmospheres, plus atmospheric physics and dynamics at this point. We're the basis for the NASA Modeling, Analysis, and Prediction Program, which encompasses the GEOS-5 and GISS models. We're the basis for a 6-year program called the Battlespace Environments Institute that encompasses Army, Navy, and AFWA, and that differs from CUAHSI in that it's research as well as operational centers. The Community Sediment Transport Model is a smaller, and the progress there has been relatively slow. That's USGS and WHOI. And I saw some Rutgers folks around who've been working with her Nanorungo a little bit. NOAA research and operational integration programs. NOAA research centers have been using ESMF as well. And there are many more. I think we have, these are the big ones. I think we have about 69 components at this point that are out in the community, that are at least at the working prototype level, and those are on our website. This is what it looks like. This is from January, so I think we have about 5 more to add. The big blue one in the middle is GEOS-5 from NASA, which componentized to a very small level. The different colors represent different agencies. So blue is NASA, green is DOD, orange is university, and red is NOAA. Pink is NSF. But you get the idea there. Again, these are listed on our website. And some more, I'll go quickly through this, some more details about some of the specific programs that we have going on. This is the National Environmental Modeling System. This is the new National Weather Service model that's being built on ESMF. And they're trying to encompass with this model both operational climate and operational weather, which is going to be quite a challenge. They have the components that they want to ESMFize are over on the right. We've done some, this Numura fish coupling was a small academic project, mostly academic project with Oregon State and some of the NOAA fisheries folks, and they were coupling a plankton model together with a fish model and a physical ocean. And they completed a prototype, and I think they're waiting to couple to ROMs now. And the last example, the WRF guys have been working on coupling to the Land Information System from AFWA, and that's intended for production at the Air Force Weather Agency. Okay. So at this point in ESMF, there are a lot of ESMF components out there. People are managing to put them together into different sorts of applications and to construct, in some cases, big hierarchical applications out of them. But ESMF is not an especially plug-and-play framework. I mean, you can have two ESMF components and you still have to do some work to get them together, both in terms of semantics and in terms of the technical connections. So what we've been trying to do as it becomes clearer what we need in order to get large-scale interoperability is to figure out what the questions are, how far people really want to go between the trade-offs, and the trade-offs between how much work you have to, how much you have to standardize versus how much plug-and-play you get. So these are some of the questions that we're facing. What aspects of interoperability are of greatest value? What levels of compliance should ESMF define? And if you have a big integration project like CUAHSI or the National Weather Service one, how much should we let them define? What conventions are needed? Do we need to extend ESMF or restrict some of its usage so that it's there are more plug-and-play guarantees? How should compliance be verified? What we're looking at doing is an automatic compliance checker over the next couple of years. And how do all these strategies and questions relate to legacy code? So we're currently, this is some information about our sort of overall project status. We're currently just within our core development team at 12 full-time staff. We usually have another 2 or 3 people hanging around from short-term grants or students or whatever. We have 2 testers. Most of our staff are remote, don't work here. And our processes and infrastructure is fully distributed. So even though most of our team isn't in the same place, it's still very tightly integrated daily communications. We have support from NSF, NASA, DoD, and NOAA, and our priorities and schedules are set via a quarterly representative change review board meeting. We get together about a dozen leads from our customer base, and they set our priorities and basically hand them off to the core team, to the development team. Not sure how much you want to see about governance, but the top level is pretty much what people would expect: an advisory board, an executive board, and an interagency group. And then the working project, we do have this change review board that sets priorities. We have the core development team that I'm the manager of, and then we have a sort of an open forum that we call the joint specification team. That's up at around 450 people at this point. That's on the mailing list anyway. And we have semi-regular telecons with those folks to do design and code reviews, to talk about their contributions. We've had a number of contributions to the code base. So that's basically the structure. All right. So last couple slides. And I should say that the timeline across the top got a little screwed up in the conversion to WebEx. So that last line on the blue box is 2010. That's the end of our current funding cycle. We started out in 2002 with ESMF with a prototype, did a pretty broad-based complete prototype with version 2, and then ended up in version 3 rewriting all of our central data structures. We're currently at about to release a version 4 that focuses more, that focuses on this physical space layer that I described, and that has the meshes and the location, and it has location streams for observational data, as well as the logically rectangular grids. We have a beta version of that out. And that's accessible through our website too. But we usually wait 3 to 6 months between our beta versions and our public releases. So our public release of version 4 will probably be this spring. And then version 5 down at the bottom, as this evolves, we'd like to see the interfaces become standard and consistent and the behavior be standard and consistent. So we've been going through a standardization process for the last couple of years, trying to do framework-wide sweeps to make sure that things are consistent across the API and throughout the implementation. All right, so this timeline is screwed up too, but this basically, the last line there is about 2015, which is where we expect our next funding cycle to end. And our first, the first items that we expect to focus on are issues of compliance and interoperability as we see the community growing across the country. What are the compliance definitions? What are the verification tools? Basically, how do we grow these distributed collaborative centers, all the NOAA labs, the NASA programs, the DoD and operational programs? How do we grow these virtual organizations into, into strongly linked bodies with good, solid identities and the ability to interoperate technically? Integration with workflows, so the web services and the semantic stuff are the first pieces of this, and introducing these pieces into other service environments are part of that. In the longer term, we have people through prototypes now exploring the idea of automated model assembly, automated coupler generation, and I guess sort of out in the 2010 time frame, maybe some of that will be maturing. Once we get, after 2010, stable interfaces, I guess that's the point at which we feel like we can really approach the academic community with a good tool in hand. Until then, the groups that seem happiest working with us are the very large centers. But basically in that time frame, I think we'd like to start an initiative that starts looking more at classroom deployment. And then the big blue bar on the bottom is just maintaining all of the numerical and computational stuff that we've developed over the years, which is a significant effort all on its own. So we expect to be around for a while. We have lots of stuff going on. It's been growing and stabilizing, and we're looking forward to just watching this all come together over the next 5 years or so. So thank you, and that's all I've got. Why don't we move to questions?
Great, thank you, Cecelia.
Sure.
Grab the hold back here a second. So, Erica, are there any questions over the phone? So if you're interested in asking a question, please dial *1. You can ask a question over the phone, and the operator will handle scheduling that, or you are free to ask. You can submit questions through the chat window, and I will be glad to read those to those attending.
Again, ladies and gentlemen, to ask a question, please hit *1 at this time.
I guess while we're waiting, folks, one of the things that I noticed, Cecelia, was how are you related, or how do you interact with the SysDems group, the Community Surface Dynamics group that's just starting up at UCAR?
Yeah, so they're not really starting up at UCAR. They're starting up at CU down the street. So we've been talking to them quite a bit. I think initially they decided to look at the common component architecture, but we've been talking to them a lot too. So I I mean, I'm not quite sure where that'll go. I've been actually on a new proposal with James Sapersky, who's leading it. So I'd say there's a good information flow there. One of the challenges that they have is that they have a lot of components in a lot of different languages, and they've got Python and C and C++ and Fortran and all this stuff. And I think one of their main objectives was to try to find a package that had an obvious way to handle multiple languages. And so CCA has a package called Babel that enables you to create, that essentially translates any of those, I believe, I'm not sure how well they do Fortran, into a common scientific interface definition language. I guess our strategy there has been to not do it explicitly, but to try to have that layer essentially be the web service layer. We're not trying to do explicit language interfaces. I think what I'd like to see is that we can create standard interfaces that can basically interact through standard protocols rather than go through a separate package. But anyway, that I think was part of their rationale for where they started out.
Okay, so there's actually a related question coming from NCSA. I think you've kind of partially answered, but I will ask you, what's the relationship to CCA? Which
right.
They're using their glue layer.
Yeah, we're not CCA and they're not us, and we don't have any projects explicitly working with them. So, it's I guess in some ways it's a similar architecture, but what specific questions were there?
It was just, I think they were asking, they want to know what's related to the atomic component architecture. I think you kind of answered with Babel.
Right.
So I guess my understanding then is that you're using web services, that kind of integrating layer.
That's right. That's the. I mean, we're currently working on our web service interface. We don't have it already. I expect we'll have it within the next year, but that's basically our interlanguage strategy.
Erica, are there any other questions on the phone?
No, sir. We have no questions on the line right now.
Okay. Yeah, I think the other thing that came up that you're dealing with, I think CUAHSI and the hydrologic community are starting to come to terms with both the HIS project, and there's a community hydrologic modeling project starting up, is about how is the dealing with all the agencies and everybody. How is that wrangling or hurting that? And any wisdom you could pass on to the hydrology community as to move to broader community-based modeling efforts?
Yeah, we managed to sort of lasso NASA, NOAA, and DOD as endorsers of what we're doing. It's having so I think that's for us the metrics of success. We have 3, plus support from NSF. It's been important. It was important for us, I think, to create a body that explicitly was for interagency coordination. So we have an interagency working group that meets really about once a year to get these folks together. Because it's really amazing to me how little they know about what the other ones are doing at the program manager level. So getting them to sit down and talk, I think, has been beneficial. And I guess what we ended up with at the end was this new operational consortium as one byproduct, maybe, of that activity, where NOAA and NASA and DOD actually created a formal agreement to say, yeah, this is the framework that we're going to use.
Okay. Erica, are there any questions on the phone?
No, sir, there are no questions.
Any other questions out there coming up through chat?
I mean, I guess I have a question for you. I mean, how do you think this relates to CUAHSI?
Well, as a kind of, there are two initiatives. I think several initiatives coming up. And I think this is really informative of. One is we have there's an initiative starting with this community hydrologic modeling platform, and I think we've been talking a lot with the system folks about and how do we start to build community level models, much as what you're doing, getting folks to start integrating modules and components and of different research projects they're working on. The other pieces that we've got is this hydrologic information system, HIS, which is a data storage model, ODM. I think Kim, if you want, Kim Schroeder, who's at Utah State, if you want to jump in and fill in some of my misconceptions, that would be great. But again, the idea is to build up a standardized data storage mechanism with supported by web services and a web interface to try to improve the data access and usability across multiple users and multiple sites.
Right.
And I think we've been talking here in the office about the possibility of a hydrologic kind of data center. One is we have similar problems with metadata and trying to coordinate, especially with the HIS project, trying to coordinate metadata and come up with a standardized metadata system, or at least to be able to translate between, do some semantic mapping between various metadata systems or agencies and institutions that hold water data.
Yeah, that makes sense. What does that community look like that is creating that metadata?
Most of it right now is coming out of the HIS group, which is headed by Dave Tarbotten and Dave Maidment. Dave Tarbotten's at Utah State and Dave Maidment's at the University of Texas.
Right. Okay.
And so they've been taking lead because they're the ones who are developing this database where you need to have the metadata to be able to understand what's inside the database.
I see. So is it incorrect to think of CSDMS as sort of the modeling branch of CUAHSI, or do you guys have your own separate modeling?
System is completely separate from us.
Okay.
I know that we've gotten involved. I guess there's a hydrology sub-working group that we've got involved with, or at least there's folks in the CUAHSI community that are participating in that. But,
yeah.
No, that's a wholly separate. That's nothing to do with. SITEM is you know, as you said, is a University of Colorado project.
Yeah.
And we're trying to learn from them because they're ahead of us and they're doing some things that at least the way that they're doing some things that I think we're interested in trying to do or expand with the hydrology community.
Right. Okay. So what? I probably should take this offline maybe, but is there a quick summary of what modeling activities, like sort of, do you have an integrated modeling activity going on? And if so, are you using OpenMI or something?
We're in the process. There's an initial working group kind of workshop last winter called CHIMP, the Community Hydrology Modeling Platform.
Yeah.
Larry Murdoch, who was on the call earlier, has been involved with that. Jay Falmietti from University of California has been involved.
Yeah.
And so that's just getting going, and that's kind of, I think that will start moving forward once we get our renewal funding established with NSF. So we're just at the beginning phases of this, getting these multi-point kind of multi-entity modeling frameworks going, which is why your presentation today is so important for the community.
Got it. Okay.
See, Erica, are there any other questions on the line?
Yes, we have a question which comes from the line of Kim Schroeder. Please proceed.
Yes, I just thought I would put in a few words on the HIS if you had any more questions on that. The HIS system is really, at its core, a protocol for communicating data with a lot of tools to that take advantage of people who are using that protocol, including a registration system that if you are using that protocol with your data, you can register in the national system, and then we're putting together a national search capability, which will then allow you to look for data across all of the systems from all of the groups that have registered and are using the protocol.
Right, so, that sounds great. That sounds just like what ESG has done with climate, really.
So
with climate data.
Project data.
Yeah. No, that makes sense. And I think where the climate community is they're now trying to link the system that they set up like that with the models themselves, with the
right.
data producers themselves.
And one of the things we have also done is we are creating an OpenMI interface to our data transfer protocol, so that once we get all this together, anyone who's using OpenMI compliant models can access all of the WaterML compliant data.
Yeah, that sounds great. I mean, one of the reasons why we're doing the Windows port is so that we have, at least it would be a step towards the OpenMI folks. So that would be really nice too. We'd love to be able to interact with them. Yeah.
And our WaterML protocol is all web service based.
Right.
So once again, sounding very familiar.
Right. Exactly. Yeah. Well, it's really interesting to hear to hear more about what you're doing. If you have a mailing list or anything, I'd love to be on it, just to learn what's going on.
We also have a website, his.CUAHSI.org.
Okay.
So, and on there's a feedback page where if you put a message in there, we'll get you on the mailing list.
Okay, super.
Okay, there are no further questions.
All right, then. Thank you, Cecelia. Thank you very much.
Sure.
Appreciate you taking your Friday afternoon out to talk with us. For folks online still, just want to remind you again of the upcoming CUAHSI activities. November 7th is a cyber seminar with Edward Rutherford from the University of Michigan. November 14th is Iris Georgakakos from Georgia Tech. And you're all invited to the member meeting and reception at the Fall AGU coming up in San Francisco. So thank you all very much, and have a pleasant weekend.
Thank you. Bye-bye.
Thank you for your participation in today's conference. This concludes the presentation. Everyone have a great day.